is from all the states of the India, Kazakhstan, Philippines, Taiwan, Malaysia, Bangladesh, Uganda, and Sri Lanka. Now I introduce Professor S.K. Prasad. He is the speaker of the today's event. S.K. Prasad is professor and head of civil engineering at VVCE Mysuru since 1st June 2020. Before joining VVCE, he worked for 32 years at SJCE Mysuru and 3 years at MS Ramaiah College of Engineering, Bangalore. He is having over 36 years of teaching and research experience. He obtained his bachelor degree in civil engineering from the University of Mysuru, securing the first rank in 1982. This distinction earned him 4 gold medals and 6 cash prizes from the university. He obtained his master's degree in geotechnical engineering from Indian Institute of Technology, Kanpur in 1985 and doctoral degree in 1996 from University of Tokyo in Japan with scholarship from Asian Development Bank. He was the visiting teacher from IST, New Delhi. He was visiting assistant professor at Asian Institute of Technology, Thailand for January 2006 term. He has published over 170 technical papers in national and international journals and conferences, guided over 70 master's dissertation and guided 3 doctoral students. Presently, 3 more students are working for PhD under his guidance. He has completed several sponsored research projects from JSS, MEP, AICT and DST. He has delivered invited lectures in Japan, Malaysia and Singapore and was chairman and keynote speaker of technical sessions at many conferences. He developed earthquake engineering laboratory at SJCE and designed and fabricated manual sacking table and weight sounding equipment. He is serving Indian Geotechnical Society for the term 2021 to 22 as the member of National Executive Council. He successfully organized Indo-Japan workshop on earthquake geotechnical engineering at Kochi during December 2012 and many national and international events. He led SJC as one of the best performing institute in TVQIP2, a World Bank assisted Government of India project as the coordinator, in which he successfully utilized rupees 1600 lakhs for implementing procurement, interaction with the industry, R&D and other academic activities. He was a member of National Technical Committee on Natural Disaster Management and Mitigation of Indian Geotechnical Society and is a member of Technical Committee 203 Geotechnical Hazards and Earthquake Related Problems of India International Society of Soil Mechanics and Geotechnical Engineering. He offered Gyan program in December 2018 on geotechnical engineering for disaster mitigation with Professor Ikua Tuhata. He delivered 5th Madhav lecture series of Indian Geotechnical Society Hyderabad chapter at JN2 Hyderabad on 1st October 2016 with a recognition as outstanding performer in the field of geotechnical engineering. He was honored by Institute of Engineers, Mysuru Center during the 51st Engineers Day celebration as outstanding achiever in civil engineering in September 2018. He delivered the prestigious 27th Professor B.K. Ramaiah lecture at ISC Bangalore on 29th March 2019 under IGS Bangalore chapter. We do have the very renowned speaker today, Professor S.K. Prasad. I request him to start his speech. Professor S.K. Prasad.
Thank you. Thank you, Professor Chandresh Solanki, for nice and elaborate introduction. I really appreciate, and I have always been a very good friend of Surat. I enjoyed your hospitality, and I still remember IGC 2019, which you conducted, gloriously. My respects to all who have gathered here. I see Dr. Parthasarathi. I see Professor Purnananda. I see Dr. Jigisha. Probably, Engineer Hitesh Desai will join soon. And the student leaders, Manali and Nazim Ali, several of you. So it's always a pleasure to be associated with the IGS Surat chapter. So if you kindly permit me, I will share my screen and then continue my lecture.
Yes, sir. You may share your screen and continue level. You may share your screen and continue your lecture.
Yes, sir. Yes, sir. I'll do that. And just to avoid any imbalance, I will turn off my camera. Okay. Is my screen visible?
Yes, sir.
And am I audible?
Yes, sir. Clearly
Alright.
audible.
Oh, thank you very much. So once again, thanks to IGS Surat Chapter as well as the Student Chapter of SVNIT for giving me this opportunity. I called this lecture as Liquefaction Risk Management. Well, I'll be showing a number of pictures, most of them I collected from internet. So I'll have to thank all those who have sourced these pictures. Basically, the objective here is to share the knowledge. So I sincerely thank all those who have, put those pictures and information on the internet. Not sure how much of these I will be able to cover. And I just have a brief introduction about earthquake geotechnical engineering. And then I'll be talking about liquefaction, the mechanism of it, the consequence of it. And since it is Gujarat, I'll be I have talked many a times, but I'll still be speaking about one of the earthen dams which suffered damage during the Bhuj earthquake in 2001. I'll be briefly talking about the impact of liquefaction in 2010 and 11 series of earthquakes which happened in Christchurch, New Zealand, some mitigation measures and evaluation of liquefaction potential. Friends, we all know that India is not free from earthquakes, especially those in Gujarat and those in the northern India, also northeast, know that earthquakes can be very, very dangerous. At least 60% of our country is considered to be seismically very active. We have had our share of bad luck due to many earthquakes. Some of them I have listed here. And Bhuj earthquake of 2001, 20 years back, really was an eye-opener to all of us to learn that, earthquakes can be disastrous and we'll have to think about earthquake disaster management. 29 cities, including Delhi, and 9 state capitals are in seismically very, very active zones. And hence, we have many urban facilities which are earthquake prone. We have to be careful. I don't have to mention what an earthquake is, but all of us know that earthquake is the vibration which is caused at the ground surface because of some disturbance which may happen at some depth below the ground surface. And this disturbance causes waves which travel all along. And these waves, when they come and hit the ground surface, there will be vibration. Major speciality of earthquake is that, it is unpredictable. We just cannot say when the next earthquake happens, where it happens, at what depth, how long will be the shaking, what will be its magnitude. So nothing is certain. But all of us know that earthquake is a 3-dimensional shaking. The vibrations are random and vibrations are cyclic. And, it is all the force earthquake force is time dependent. The biggest challenge is that, no two earthquake motions are similar. Same earthquake at two different places, we have different levels of shaking. Same place during two different earthquakes, totally different earthquakes. Therefore, it is a big challenge for us to predict what will be the next earthquake. And earthquake engineering is, multidisciplinary. The objective is to reduce the damaging effect of earthquake, to reduce the loss of life. And in this regard, majority of civil engineers plus others work together to reduce the damaging effect. So we have geologists who will talk about the happenings below the ground. A geotechnical engineer will perhaps, be in between the structural engineer and geologist, talking about the, behavior of ground near the surface where we put the foundation and so on. Structural engineer will be more concentrating on the superstructure, of course, also dealing with the soil structure interaction along with geotechnical engineers. I always try to show this slide whenever I talk about, engineering, civil engineering or geotechnical engineering. Soil is the most complex construction material. What do I mean by complex? It is very difficult to understand soil. Maybe steel, we can say how much load it can carry. Maybe concrete, we can say at what load, at what force it fails. But it is very difficult to predict how soil behaves because of many of the uncertainties which I have listed here, all those in green. Yet, I always say that soil is a smart material. Soil is an intelligent material. And the reasons for that is, all of you agree with me that soil is colorful. It exists in different colors. It is sensitive. Some soils are more sensitive, some are less sensitive. If you allow them to stay in their place, they have good strength. But if you disturb, their strength reduces. In some cases, strength may reduce to even zero, which we call as, hypersensitive clays. Soil has memory. It knows what load, what pressure it was subjected to before. Present pressure, if it is more, it behaves in some way. If it is less, its behavior is totally different. Soil changes its properties with time. Example, water content. During summer, water content could be even close to zero. On the other hand, during rainy season, it can be very high. Just compare these characteristics with human beings. They match. Therefore, I say that soil can be compared with human beings, and hence, I say that soil has life. So what does it mean? It means that, if you respect soil, it behaves according to your taste, your requirements. If you disrespect, it misbehaves. It shows as a failure. So we all should know about it. And therefore, whenever we deal with geotechnical engineering, we have to respect soil. Many a times we may not be experts. I'll say, don't bother. If you are not an expert, consult an expert. You should at least try to know that it is a soil which is difficult to handle. So with this brief note about soil, and then, today geotechnical engineering has occupied vast area. So there is nothing which, you can do without the help of geotechnical engineering. Lot of activities do happen on ground, below ground. And these are all the list of geotechnical structures which play important role in infrastructure. Now, when an earthquake happens, it happens at some depth below the ground, and the waves do travel. Waves do travel through rocks. Waves also have to travel through soil. And soil, in general, geological origin, it will be in the form of layers. And hence, each layer has different properties. And when these waves travel through these waves, through these layers, there is a possibility of reflection, refraction, deflection, and so on. And there will be multiple reflections and so on. And by the time the waves reach the ground surface, there is a possibility that there is an amplification in the ground motion. In addition, at the boundary, new surface waves are generated, Rayleigh wave, Love wave, and all these amplify the ground motion at the surface. Therefore, what kind of ground motion we have in the rock can be very different from the kind of ground motion we have at the below the soil, on top of the soil. And all this ground motion at the surface of the soil depends upon the type of the soil through which these waves travel. And it is a big challenge for a geotechnical engineer to assess what will be the type of motion at the ground surface, below which there may be 10 meter, 20 meter, 30 meter of soil. So when these waves travel through the soil, the soil particles are subjected to sufficient amount of shear force, and waves do travel upwards and they hit the foundation with a sufficient amount of horizontal force, which is time dependent. So then the structure will behave according to the kind of force it is subjected to. But how this force comes? This comes through the soil, and hence it is dependent on the type of the soil. Always remember, a soil at some depth below, let us say below a horizontal ground level, will be subjected to confining pressures. Okay, these are the principal stresses. So this is the vertical stress, and the horizontal stress will be K times the vertical stress. K sometimes can be more than 1, less than 1, depending on the situation. K is the coefficient of earth pressure. And when an earthquake happens, in addition to these vertical and horizontal stresses, there will be shear, because the shear waves do travel through the mass, and there will be shear additionally. So a element of soil will be subjected to only vertical and horizontal normal stresses under normal situations, when of course it is under level ground. And during an earthquake, it will be subjected to additional shear stress. We should always know. And this additional shear stress will be in one direction at one instant of time, and it will be in the opposite direction at the next instant of time, as I have shown here. Therefore, it continuously shakes, causing a shear like this. Therefore, what happens to Mohr circle? Mohr circle will be of smaller diameter before the earthquake, and it will have an increased diameter depending on the shear stress. Okay, if the earthquake is big, if the epicenter is closer, and if the soil has the ability to shake rigorously, the value of shear stress will be large. So this aspect all of you should know. And this shear stress, additional shear stress, is the one which causes different kinds of problems associated with earthquake geotechnical engineering. So in a very simple way, when the shear stress is small, very small, maybe the variations are linear, so you can plot a graph between the shear stress and shear strain, and it will be something like a straight line, stress strain curve. On the other hand, when the shear stress is large, the stress strain curve will no longer be a straight line like this, it will be in this form. Okay, and this looping depends upon the damping of the material, and soil is one which has sufficiently large amount of damping. The area of this loop will indicate the amount of damping. Damping is some kind of sluggishness. So whenever we plot a graph between the shear modulus and shear strain, you will know that at very low strain, the shear modulus will be large. And when you increase the strain level, shear modulus continuously decreases, and it will perhaps be very close to 0 or very low value when the shear strains are more. On the other hand, damping will be very small value at low strains. It increases sufficiently when the strain level increases. Please note, the strain level increases whenever you subject the ground to rigorous shaking during earthquake. So bigger earthquakes, the strain level can be very high. So otherwise, in normal circumstance, strain level the soil is subjected to can be in the range of 10 to the power minus 6, at the most minus 5. But under large shaking, it can go to 10 to the power minus 3, minus 2, and so on. So strain level increases, stiffness decreases, damping increases. So these changes in properties you should know, and hence these lead to several effects on the ground. The primary effect of earthquake is to cause ground breaks, fault formation. The secondary effects can be liquefaction, landslide, failure of foundation, failure of waterfront structures, failure of retaining walls, failure of bridges, earth dams, embankment failure, tunnel failure. And the other secondary effect can be tsunami, which all of us are familiar with, siege in a closed body, a closed water body, and so on. So friends, I already told you that soil is a very complex material, construction material. And I also told you that earthquakes are unpredictable. What you study in earthquake geotechnical engineering is the effect of earthquake on complex soil, effect of unpredictable earthquake on complex soil. So you know how difficult the situation is, how much of challenge will be there, how much of uncertainty will be there. So earthquake geotechnical engineering has evolved over years. It's a very new topic compared to the rest of the classical geotechnical engineering. And only since 1964, this has developed tremendously over the last 50 to 55 years. There has been a considerable development. And today, we can claim that we have good confidence in dealing with, effect of earthquake on ground. Even in India, lot of work has been done of late since 1995 or since 2000. And today, almost every research laboratory has been actively working in the area of earthquake geotechnical engineering, and I'm very proud of it. Well, in general, disaster management means, reducing the risk of the disaster. And please note, I always try to give this simple equation: hazard plus risk can cause disaster. Hazard is something which is not under our control. Hazard is earthquake. We cannot stop an earthquake. We cannot control an earthquake. But risk is totally ours. So only when these two combine, we'll have disaster. So how do you reduce disaster? Since hazard is not under control, risk is what we have to manage. Risk is what we have to control. So risk is man-made, and there may be risk because of various things like explosion in population, unscientific construction, irregular growth of cities, industrial development in a very poorly managed way, lack of free space, environmental pollution, and so on are all risks. And if we can keep risk down, we will definitely stop the disaster or reduce the disaster effect. And if you can make risk zero, you have achieved your goal. And that is what is very important. Therefore, risk management plays a very important role in almost all the disasters. So here risk management refers to, forecasting and evaluation of the risk together with identifying the procedure to minimize that. So in this present scenario, I'll be talking about identifying the, what is liquefaction, how do you identify it, what is the extent of damage an earthquake, a liquefaction can cause, and how we can mitigate. These are the things which I plan to deal with in the next maybe 30 minutes, 40 minutes or so. Liquefaction. Well, I keep showing these pictures. This is what happened in Turkey, Adapazarı earthquake in 1999. This building was comfortable, okay, on a ground which was stable before the earthquake. You can see what has happened. The structure looks perfectly okay. So structural engineer has done his job well. But unfortunately, the structural engineer and geotechnical engineer failed to recognize that this soil can liquefy at some point of time. And hence, the structure was standing on a liquid at the time of earthquake or just after the earthquake, and effect is this. This is in Kobe during 1995 earthquake. This is an open drain, and you can see the floor of the open drain. It is being lifted up. Why is it lifted up? We will see a little later. The water which is below the groundwater, it rises up, and at a very high force. And this floor was not designed to take that force, and hence, like fountain water came out, and all this water is the one which has come out after the liquefaction, after the earthquake. This one is an island in near Kobe, man-made island called Port Island, and this is a retaining wall on the edge of the island. This island was built sometime in 1970s, 60s, 70s or so, 70s to 80s, and then 1995 this earthquake happened, and because of that, the wall, the retaining wall, the key wall, it moved towards sea by sufficient distance, and hence the backfill was considerably, it experienced settlement. This happened because the backfill liquefied. This is a famous dam failure. So this is Lower San Fernando Dam, and this failure happened in 1971 during the San Fernando earthquake in California. Fortunately, upper San Fernando Dam was safe, and luckily there was not much of water in the reservoir. The Lower San Fernando Dam's base, the foundation soil, it experienced liquefaction here, and hence when the base is gone, when the base becomes liquid, you can imagine what happens. So the entire dam material, it slid down. Luckily, less water on the upstream resulted in less damage, but this is a famous failure which even today is studied. These two bridges, you can see that the deck slab has become a slide. That is because of the relative movement of the piers. Piers are built on foundations, okay, which are on the foundation soil, and if the foundation soil becomes weak, like liquefaction, you can expect the relative movement of them. And normally, whatever bearing is given, okay, this bearing was not sufficient. Available bearing was not sufficient, and hence they slid down. This happened in 1995 in Japan, Port Island, and similar thing happened even in 1964 again in Japan, in Niigata. So the top one is Nishi Bridge and the bottom one is Showa Bridge in Niigata. So you can expect similar types of failures, but you'll have to understand, you should learn the lesson and try to think of rectification. Possibly, the bearing, they could have increased the bearing area, or they could have fixed the deck slab, and it could have been designed in a different way. Well, friends, after talking about some of the effects of liquefaction, I just would like to give some, speak for a while on the mechanism of liquefaction. As I said, liquefaction is the liquid-like behavior of soil. So you can imagine that when soil becomes liquid, what will happen to shear strength? Automatically, shear strength becomes zero. Why? Why will it behave like liquid? It is because of the development of excess pore water pressure. Please note that soil mass has pore water in its pore space, but that pore water will have excess pressure. And that excess pressure, when it reaches a value equal to the initial confining pressure, the effective stress in soil will become zero. And that is what is liquefaction. That is what is liquid-like behavior. That is when the shear strength in soil becomes zero. So just imagine you have soil in a cylinder. Put that, take sand, put it in a cylinder, and then put the cylinder containing sand on a vibrator. Rigorously vibrate, shake it. What will happen? Normally we tend to say that it will densify, and hence, volume will reduce. But soil is a very peculiar material. If you are a thorough geotechnical engineer, the first question you will ask me is, how is the initial condition of the soil? Has it been loosely kept or has it been densely packed? See, if it is very loosely placed and put on the vibrator, it will densify. On the other hand, if it is, densified to its maximum capacity, and if you keep that on the vibrator, please note, soil is an interesting material. It will dilate. It will increase in volume. Okay, that point you should know. And here I'm talking about soil which is loose. And when you put it on the vibrator or when you shake it, automatically it will compress. It will densify. Now imagine that you have the same soil kept in the cylinder and kept on the shaker, but in addition, that is saturated. So entire void space is filled with water. Imagine that it is fine silty sand, then there is less space in between them. Therefore, water cannot very freely move out. Okay, they are all packed loosely, but water cannot easily move out because of the contacts, continuous contacts. When you keep this system on a vibrator and shake it, water wants to come out, not much space for it to come out, and hence water will be under pressure, and it exerts pressure on soil and tries to push the soil particles away. When that happens, the contact between the soil particles is lost. Whenever the contact is lost, you can imagine that there will be no strength, because soil, particularly cohesion loss soil, gains strength only by the number of contacts. And momentarily, these number of contacts would be reduced. In the worst situation, it can even be zero, something like this. Slowly, this water tries to escape, because water is a clever material. It doesn't want to be under pressure at all. It escapes out through some weak zones. And once it goes, when water goes out, naturally volume reduces and the soil particles will densify and occupy a more stable position. So please note that this was the initial condition, loose soil. And after liquefaction, it becomes densified and there will be enormous post-liquefaction settlement. During liquefaction, this is the during liquefaction period, water will be under extra pressure. That's what I called as excess pore water pressure. This results in loss of the contact between the particles momentarily. And when there is no contact, this is a fluid of higher density, that's all. And you know how a fluid behaves. You know what will be its shear strength. And this is how the mechanism of liquefaction can be explained. So you have a structure built on loose sand, saturated sand. Whenever there is earthquake, there will be vibration. And due to this vibration, momentarily, the particles of sand, will lose contact between them. And hence, slowly, the water from here goes out. This process we call as sand boil. And it doesn't go out at all places. Wherever weak zones are there, it goes out. Therefore, the settlement of the building can be uneven. So it cannot be uniform settlement. And it all depends upon how the ground takes the shape. And finally, you will see that the ground would have densified. Ground would have experienced large amount of settlement. We all are familiar with this equation of shear strength based on Moore Coulomb's criteria. Tau is equal to C plus sigma tan phi. If I express this in effective stress approach, tau is equal to C prime plus sigma dash into tan phi dash, C prime into sigma prime plus sigma prime into tan phi prime. What is sigma prime? It is total pressure minus pore water pressure. That is sigma minus U. And pore water pressure during earthquake, okay? Pore water pressure during earthquake will increase. And due to any reason, if this value increases to a value equal to sigma, that is initial confining pressure, this entire bracketed term will be 0. And if the soil is cohesionless, this also is 0. So even if the soil has friction angle, this is 0, this is 0, tau will become 0. And that is the situation of complete liquefaction. So at liquefaction, please note that soil which has a number of contact points, as seen here, will lose the contact because the particles will be separated out because of the excess pressure, the excess pore water pressure, created by the water here. If you keep a piezometer in earth during earthquake, piezometer reading will be very large. That means, it clearly shows the pressure in the ground. So you can see this is what happens. So you can see that the particles are losing contact with each other. Of course, it is momentary till water is able to go out. If water cannot easily go out, automatically that water will be under pressure. So that's what I have tried to show here also. So this is the soil particles, which are fairly loose, and hence, these are all the void spaces filled with water, saturated with water. And during earthquake, this pore water will be under pressure, and it simply pushes the soil particles out. And slowly, after liquefaction, water gradually goes out, and this process we call as sand boiling, and hence, the ground will experience settlement. If the settlement is uniform, the hazard can be reduced, but it will not be uniform, and hence, you can expect hazard of any kind. And if it is uneven, even the superstructure may fail, causing huge infrastructure loss. Once again, I try to mention that soil is a very peculiar material. You have soil densely packed, and if you subject it to shear, there will be increase in volume, which we call as dilative behavior. This happens in dense sand. On the other hand, same soil, if it is loosely placed, and if it is subjected to shear, it is subjected to decrease in volume. There will be settlement, and this happens in loose sand. This behavior we call as contractive behavior. Very quickly, what Casagrande showed way back in 1936 in his PhD studies, he used triaxial cell. He did the test on sand. Okay, he did the drained strain control test. And, if you plot stress versus strain, deviated stress versus axial strain, in dense sand, you will notice that you will reach a peak value, ultimate stress, of yielding, and after yield, it reduces. And then, when the strains are large, it becomes, almost constant. It cannot reduce further. This is the minimum shear stress it will be deviated stress it will be subjected to under very, very large strain. Interestingly, same soil you take in loose state and do the test, you will notice that there will not be a peak. It is loose sand. It will never show peak, but under large strain, you will see that the deviated stress here also will be constant, same. It will not change. If I plot a graph between deviated stress and void ratio, dense sand will have low void ratio initially, and when you subject it to large shear, the void ratio increases, and you'll have the path going something like this, and it stops here. Similarly, loose sand is having large void ratio initially, and when it is sheared under large strain, it will have some constant, deviated stress at a given confining pressure. So at different confining pressures, you will have, large strain void ratio, which is a constant value, whether the soil is in dense state or loose state. And if you plot a graph between the void ratio and confining pressure, you will see that the graph is something like this. This is called CVR line, okay? Critical void ratio line. If I plot confining pressure on the logarithmic scale, this line will be a straight line. So any soil initially, above the CVR line, critical void ratio line, we say that, it is in the loose state. And when it is subjected to shear, it will show contractive behavior. On the other hand, a soil which is below CVR line, it is said to be in dense state. And whenever it is subjected to shear, it experiences increase in volume, shows dilative behavior. So naturally, undrained behavior is, no volume change. Therefore, a soil from here will reach a critical void ratio, going horizontally like this. This also from here, it goes, in undrained situation, no increase in volume, no change in volume, and reaches a void ratio like this. On the other hand, if you allow drainage, it will follow some path like this and reach a critical void ratio like this. However, CVR line is a constant line. Whether the soil is in dilative stage or contractive stage, behavior is similar. So why I mentioned this? A soil of this kind, dense sand, will not liquefy. On the other hand, a soil, this here, dense sand, it will not liquefy. On the other hand, soil above CVR line, which is in loose state, has the tendency to liquefy. So please note, if at all you are looking at mitigating, the best thing you should do is densify the ground. So whichever soil is in the contractive stage, in the initial stages, is likely to experience liquefaction. Well, I just tried to show a number of cases of liquefaction. So this is one of the biggest earthquakes which has hit the globe. It stands at 4th or 5th place, 2011 March, magnitude 9. And this earthquake happened in sea, almost about 350 kilometers away from Tokyo City in Japan, in sea. Okay. And it had a magnitude 9. Unfortunately, it killed 25,000 people. And most of the deaths were because of the tsunami. Tsunami waves had heights equal to 20 meters or so. And any earthquake, you see this graph. A civil engineer is familiar with this graph. So in this graph, on the vertical axis, you see the ground motion in the form of acceleration, velocity, or displacement. Popularly, we put acceleration. And on the horizontal axis, time. This earthquake near the epicenter, okay, epicenter was, in sea. Sendai is the closest city, about 50-60 kilometers away from the epicenter. Near the epicenter, the shaking was for a period of nearly 5 minutes. This was one of the longest earthquakes to have happened. The strong motion part itself, the continuous shaking, and the rigorous shaking part was itself for a minute or so. And, earthquake happened in, about 350 kilometers away from Tokyo. But, so far away, even Tokyo City or near Tokyo City, many places were subjected to liquefaction. Whatever I show here in red shows liquefaction. So I have taken acceleration sensors, one in a liquefied zone in a place called Inage, somewhere here, and another in a place where it did not liquefy, Urayasu. Okay, so 2 acceleration sensors, and these are the records. They were at distances of about 20 kilometers or so, not far away. So same type of earthquake force, but you can see the changes in the behavior. So what I want you to note is that this is the portion which liquefied. So the wave, here, it keeps on moving like this, shaking. But here, after reaching here, waves actually reduced. So these are the shear waves which actually cause the ground to shake. And, shear wave velocity reduced, and, the motion, became both weaker, and period got elongated. So the wave period was elongated. In other words, wave frequency got reduced considerably. So this is the zone where liquefaction happened. And because of the liquefaction, sometimes this entire area will be even, still. There will be no shaking at all. So vibration totally nullifies in many, many situations. So consequence of liquefaction. What happens due to liquefaction? So very quickly, you can see extraordinary settlement, Some of the buried structures may be lifted up. There may be changes in the lateral earth pressure. Ground may oscillate. There may be failure of the slopes, bearing capacity failure, sand boil, whatever I mentioned. Sometimes the ground may break. There may be fault-like formation. So all these things I will try to show in pictures. So I did several tests at my previous institution. I built this shaking table, manual shaking table, and I spent about 10,000 rupees, but it can do the work of a rigorous, sophisticated shake table. I'm putting a container and the soil here. The total weight of soil is about 750 kgs. This is 2 meters long. This is 0.6 meters high and 0.5 meter wide. I made loose ground here, and just to try to see the deformation of the soil during shaking, I made these grids of 10 centimeter by 10 centimeter grid, and for that I used color sand, and coloring of sand was made using Godrej hair dye. So this is a saturated soil, and you can please see how the structure which is built on it before shaking is very stable, but the moment the shaking is given, because the soil softened, this is what has happened. You can see similar behavior in the field. This is in Niigata in 1964. This one is in Kobe in 1995. This is the shake table which I built. I will not talk about it now. See, this is one earthquake, very famous for site effect, very famous for talking about amplification in ground motion and even near resonance situation. So in 1985, in Mexico, Michoacan earthquake happened. Interestingly, the epicenter was about 400 kilometers away. Still, this place suffered several damages, including liquefaction. This 6-storied building, residential commercial building, it was built on a ground which liquefied later, and because of the liquefaction, this building sank by more than 1 meter. So it is all due to the consolidation the ground experienced immediately after liquefaction. I just want to show you how structures can be uplifted. The structures which are buried can be uplifted. Here you see a water tank in Kobe in 1995. This water tank, unfortunately, was lightweight then because there was no water in it. And when the earthquake happened, this water tank came up. You can see a Japanese standing here just to show that it came up by more than 2 feet. This one is a manhole in Tokyo. Okay, this picture was taken by Professor Tauhata, my advisor. Okay, this manhole perhaps was bored being underground, and it just found during earthquake a chance to come out. You can see how it has come out. In India, we make the manholes with brick masonry, and this is a precast concrete manhole. And during the earthquake, that buried manhole, it has come up. I'll just show you. I have here the ground. I have a buried structure inside. So before shaking, everything looks fine, but you can just see once the shaking is started, how the buried structure comes up. So this is how it comes up. So whatever happens in the field can be depicted in the laboratory, and that is exactly what we did, for the last 2 decades or so, and try to understand different behaviors. I just would like to take you on to this 1995 earthquake in Kobe. And, this is Kobe city, a very beautiful city. This is an island called Awaji Island, and earthquake epicenter was centered somewhere here. This one is a very famous bridge. It is one of the best suspension bridges you can see, Akashi Kaikyo Bridge. Okay, this has the longest span. And it was built, this bridge was built, it was not still commissioned, just on the verge of being commissioned. Earthquake happened on 17 January. And these two are man-made islands. This is Port Island. It is about, 2 kilometers away from the city of Kobe. It was built for about 15-20 years, from 1970s to 80s, early 70s to 85 or so, and very beautiful. It had many facilities, lot of good infrastructure, hotels, and then harbor facilities and so on. And all around here, it was built on some wall, so you can call it as key wall, a retaining wall. So this is another man-made island called Rocco Island. This is called Port Island. So as I told earlier, this wall, okay, retaining wall near the sea, okay, it moved towards sea by 5 meters. Why did it move? Because this backfill, it was man-made island, okay, built only about 10-15 years back. They felt that they have densified, but it was not fully dense. And during shaking, the level of acceleration was very high. Awaji Island was very close, epicenter was very close. And during shaking, rigorous shaking, backfill liquefied. What happens when it liquefies? Whatever earth pressure was there, it gets increased enormously. So earth pressure increased, and hence, the backfill pushed the wall towards sea. It moved by 5 meters, and hence, this entire earth, it liquefied, and then water came out, and hence it collapsed. How much did it collapse? It collapsed by more than 2 meters. So that's the effect of this. Fortunately, these buildings were built on pile foundation taken into stable ground. That is why they survived. Otherwise, if these buildings were built on shallow foundations on backfill, so everything would have been destroyed. I just would like to mention here that, interestingly, so this is Tokyo Bay, this is Tokyo. These are all small, localities of Tokyo called, different cities. Urayasu city, lot of reclaimed land is there. Even Tokyo Disneyland is built here, okay, on filled up land. So extension here, reclaimed land. So it was found that during that 2011 earthquake, 350 kilometers away, majority of this area liquefied. Wherever you see carefully liquefaction which has happened, the area which was reclaimed, which was densified, maybe, more than 70, 80 years back, they did not liquefy. On the other hand, those areas which were recently densified, which were recently, reclaimed, okay, they liquefied. So one very important aspect you people should know is that, age of the, filled up ground plays a very important role. If it is filled up maybe about 100 years back, chances of liquefaction are reduced. On the other hand, latest filled up one, even if the density is same, so that is likely to liquefy. So you can see here, so this is the original land here. This construction happened between 1965 and 75, whereas this one happened relatively latest in 1980s. And this entire portion liquefied. This liquefied less. This did not liquefy at all. So age of the ground plays an important role, especially if it is a filled up one. You can just see how the oscillation takes place below the ground has liquefied. These are paver blocks. This is again in Urayasu city. You can see how the paver blocks are moved and how this tree, it is being treated. And you can even hear the noise. Okay. Man-made islands are vulnerable. Abandoned river channels, backfills, delta, filled up ground, which are young, they're all vulnerable. So you can see the effect of liquefaction on a sloping ground here. Here also, see, this was in Alaska earthquake Anchorage. Okay, this portion, this portion of the ground after liquefaction, it slid down, causing the failure of the school building. In this map, you can see elevated places. After liquefaction, the ground has simply moved all along. It moved by more than 5-10 meters, searching out for level surface. Okay, so they moved for several meters beyond. The effect of liquefaction, especially for buried structures, you can see this is a pipe which has buckled after liquefaction. It was a buried pipe which has buckled. This is pile foundation. Okay, after this Niigata earthquake in 1964, you can see that each of the pile has failed. That is because of the lateral movement of the ground. So lateral movement of the liquefied ground that pushes the piles. And these piles were designed to take the vertical load. They were never designed for taking the lateral force. And under the lateral force, they failed. Please note, even in Kandla port, Gujarat, lot of piles failed because of the liquefaction effect. So lateral force caused by the liquefied soil moving in one direction was the major cause for failure of pile foundation in Kandla port. This is another very interesting failure. Okay, these are the apartment buildings in 1960s built, in Niigata city. Very close by there is Shinoza River, and these are all from the reclaimed land from Shinoza River, and these are called, Kawagishi Cho apartment buildings, several of them. Okay, you can see how they are all tilted because all of them are built on ground which was loose and which liquefied. So some of them had moved towards this way, some of them moved this way. If you closely see, those which had eccentricity more towards the left here, they tilted that way, and these had eccentricity in this direction. The weight was more on this direction, therefore they tilted here. Only one building never tilted because this was built on pile foundation taken into stables of ground. And all these were built on raft foundation near the surface. And hence, because of the liquefaction, they all tilted to different levels. This has totally become flat. So that's what I said, Shinoza River, and it used to flow like this, forming a bay like this. Naturally, when the city grows, we reclaim land. So here, this entire land was reclaimed. And this apartment buildings, Kawagishi Cho apartment buildings, they were built on the reclaimed land. And these reclaimed lands, sometimes in 1920s also, they were reclaimed. And this earthquake happened in 1964, 30, 40 year old then. So naturally, they were not, dense enough to avoid liquefaction. Entire ground here suffered liquefaction. So these two buildings appear to be angry on each other, and you can see the effect is because this ground here liquefied. This is in Turkey, Adapazarı earthquake in 1999, and this one has more eccentric load on this side, therefore it tilted in this direction, and the other one had more eccentric load on the other side, therefore they tilted in the opposite directions because they were being built on liquid now. So naturally, they tilt where the eccentricity is. So one of the important things for a structural engineer is see that eccentricity is minimized. Okay, thereby if it is more balanced, perhaps it will not experience a tilt like this when the ground liquefies. This is what is sand boil. Okay, you can see sand boil here. I have already, time is 11 o'clock. I'll request Professor Solanki to let me know how much more time I can take.
Sir, you may continue up to 11:15.
11:15. All right. I'll try to.
Will it be okay?
Yeah. I'll try to cover up by 11:15. Thank you very much.
Okay.
So this is a typical sand boil. So this portion liquefied, and hence the soil, water here is under excess pressure. It wants to release that pressure. It finds some weak zone to move, and then it moves through weak zone, and hence fountain lake thing will be formed, and along with it, it will also carry some sand particles from here, and fountain is formed. Then these sand particles are all deposited on the sides of the hole. Therefore, you see a hole something like this. So this is what is the sand boil which we saw in Gujarat in the earth dam, which I'll be showing very quickly. So this is ground break. because the ground here experienced the liquefaction. So this is that Chang Dam failure. I will not go deep into this. This is during the Gujarat earthquake. I can spend sufficient amount of time, but I will skip this thing. I have spoken about it many a times. This is how the dam looked when we visited the site. Entire portion had actually, people said, the dam had blasted. So entire portion had liquefied, and blast-like situation had happened. And I went about 3 months later after the earthquake, and they were trying to build the dam before the next monsoon comes, so that they could store water. For almost 2 seasons, there was drought in Gujarat before that earthquake. So this is how it looked. This is the picture taken of the dam immediately after the earthquake, not by us. In February, Professor Bardet had taken this picture. So when we visited, this entire portion of the dam was removed, and we did some tests here to identify the kind of soil, what is there. So we could clearly find out that it was loose, sandy soil. So, this is the picture of the sand boil which we saw. So sand boil is the evidence of liquefaction. There were at least 5-6 sand boils which we could locate, and this is the picture which we took, and this is how we were doing the test on that day. We used weight throwing equipment to find out the stiffness of the ground. SPT N value was found to be much less than 10. Okay, so this is how we understood the mechanism of failure to be. The ground here, 3 meters approximately, experienced liquefaction. When the ground here liquefied, the earthen dam which was standing, it had no scope to stand like this because it was on the liquid, and somehow imbalance, and this liquefied ground, it was trying to move. People actually saw fountains here. So when it was moving, it moved. The dam, broke like this, and people called that as a blast. So it is all because of the effect of liquefaction. I will quickly show you the effect of liquefaction due to several earthquakes which happened in New Zealand, in Christchurch. So this was presented by Professor Misko Kubriowski, who he is my senior at Tokyo University. Okay, he presented in one of the ISSNG webinars in 2015. So September 10th, February 11th, June 11th, December 11th, many earthquakes happened in Christchurch. Okay, so this is the central business area of Christchurch, and all these are several earthquakes and aftershocks. So these are different earthquakes. You can see on September 2010, 1, 2, 3, 4, 5 earthquakes. February 2011, 3 earthquakes. There was June 2011, a couple of earthquakes. Again, December 2011, 2 earthquakes. So all had magnitudes, between 5.5 and 7.1. The interesting part I want, this is in the central business area, not very far from sea. And there, 20 meter of soft overburden soil. This is about 2 kilometer by 2 kilometer area. And this is how the water table looked. Water table was close to the surface. So entire area was saturated. So what I want to show here is that, all this area were liquefied during not one earthquake, many earthquakes. One of the important lessons learned from this earthquake, this series of earthquakes, is that already liquefied soil, will it liquefy, was one of the serious questions. Yes, that can happen. So it is shown here. This is one of the hockey grounds, okay, which liquefied in 2010 September. Same area showed liquefaction again in 2011 March. Similarly, this residential area, this entire ground, this liquefied in 2010 September, 2011 February, same area. Again, repetition. They had made some pavement here, but this ground, this portion of the ground which was left open, this liquefied in 2011 April. Similarly, June 2011 also it showed liquefaction. You can see that lawn is grown, but still, the ground here is liquefied. So in 2011 June, again in the second part, entire area shows liquefaction effect. So already liquefied ground can liquefy. This is one of the important lessons learned. So you can see the effect of liquefaction here. So very quickly, can all soils liquefy? No. For liquefaction to happen, soil should be fine cohesionless soil. It should be 100% saturated. It should have low permeability. The shaking should be enormous for a long duration. Please note that soil should be extremely loose. And I have also added, if it is of recent deposits formed only 5-10 years back, it is more vulnerable. All these situations make the soil vulnerable to liquefaction. So to avoid liquefaction, you should think of avoiding these situations. So there are, many factors which influence liquefaction. I have listed them, and maybe because of lack of time, I will avoid. See, this is in Niigata, picture taken in 1964 by this person, Yumina Mochi, from an aircraft immediately after the earthquake. And, this is one of the first live pictures taken during liquefaction. So I'll skip this. Well, mitigation. These are all the different mitigations possible. Again, I will not be touching on these things. One of the important mitigations is densification. Even by providing proper drainage, allowing for free movement of water, because excess pore water pressure is the main cause. So if you can allow the water to go out also, possibly liquefaction can be avoided. So these are all different lists of this thing. So one simple thing we can think of is, studies have shown that you have layered soil. This layer is likely to liquefy. If you have a thicker non-liquefiable layer above, the effect of liquefaction of this is not felt on the ground surface, especially if it is not an extremely important structure. If it is a residential area, what you should think of is to provide a thicker non-liquefiable ground. How thick it should be, I have mentioned here. Okay, this is the picture by, research by Professor Ishihara. If you have magnitude 6 earthquake, the thickness of that can be 2.5 to 3 meters. Magnitude 7 earthquake, 5 to 6 meters. Magnitude 8 earthquake, 8 meters thick. Okay. Similar work by Professor Tauhata. So he says, if it is more than 2 meter thick, that is the top layer, maybe the opportunities are that it will not fail. So you can think of making the top 2 or 3 meters densified, or you can probably remove water, continuously keep it pumping, keep pumping out. You can use any method. And if you have the top layer, unliquefiable, non-liquefiable, you have achieved your goal. So the other important thing you can think of is, if you confine the structure, if you don't allow the water to move out sidewards, you also have achieved your goal. This was done in one of the hotel buildings, in 1995 Kobe earthquake. Several portions liquefied, but because this mitigation measure was followed, this survived. So one thing you can do is, if you have, let us say, a series of housing already existing, if this is the road surface, along the road, you can confine. You can just build some kind of a wall. You can use some ground improvement technique. You can solidify and build this wall as a entire area, and tell the individual building owners to also build some wall like this. It becomes fairly economical. And even if the ground inside liquefies, water cannot move out easily. Therefore, the building will be safe and stable. So you can think of mitigation in different ways. So I just wanted to tell that, IS code 2002 to, when it was revised to 2016, some effort was put on liquefaction. So it was mentioned that, type D type of soil, which is considered to be unstable, collapsible, or liquefiable, okay, needs to be engineered better. Some kind of ground improvement is required, and you have to identify whether what is the liquefaction potential here. So it is suggested that 1971 seed and Idris formula can be utilized, and today we have different efforts by different people. So usually cyclic stress approach is what we follow. Seed and Idris, proposed their modified formula 2003, Idris Bolanger in 2008. Basically, they have addressed the problem of possible liquefaction of fine grained soils also, and they also addressed the post earthquake reconsolidation settlement. So it's a very simple, very logical method of identifying, okay, whether the ground at any particular depth is liquefiable or not. When the factor of safety becomes less than 1, we say that it is prone to liquefaction. So I quickly end my lecture. Okay, I tried to talk here about different effects, and those of you who would like to take up research in the area of liquefaction, liquefaction is a very interesting topic for all geotechnical engineers. Are is, you have soil which is relatively solid, and when it liquefies, it becomes fluid. So lot of changes are possible. So will already liquefied soil further liquefy in future earthquakes? Yes, it has already been shown, but you can probably try to prove why and how it happens. Will aging of man-made fills reduce liquefaction potential? Yes. Same fill, if it is 100, 150-year-old, less chances of liquefaction. Can confinement be a good mitigation measure against liquefaction? Yes. So you already have existing buildings and you want to think of mitigation. One of the simple means is you try to provide a wall-like situation around the foundation. So that will help. Can thicker top non-liquefiable layer reduce the damaging effect of liquefaction? Yes. You may have a ground which may liquefy below at some depth. If you have at least 2 to 3 meters thick non-liquefiable ground, then chances that the building will collapse are reduced. Do silt and clay-sized soil materials liquefy? Yes, a lot of research has gone by, and the recent, methods, efforts by Idris Bolanger suggest that. Well, I also added here, can gravel liquefy? Yes, of course, gravel also can liquefy if it has similar conditions. That is, contractive behavior, saturated condition, no scope for water to come out. Normally, gravel has extremely big permeability, large permeability. If you don't allow water to go out, that also can liquefy. So with this, I just summarize mentioning that, liquefaction is a very interesting phenomena. And we talked about the mechanism of liquefaction, what is the consequence of liquefaction, what are the typical failures during liquefaction, what factors influence liquefaction. And though I couldn't touch much on mitigation and evaluation of liquefaction potential, and these are the important topics here. I need to close here, and I sincerely thank each one of you for your patient listening. I thank the organizers, IGS Surat, NIT, SVNIT, and then, the student chapter of SVNIT for giving me this opportunity to make my presentation. Thank you, one and all. So I have closed my discussion, and maybe I will stop presenting. I see Engineer Hitesh Desai. Sir, very, very good morning. I am extremely happy to see you.
Good morning, sir. What I am thinking that for the next thing, I think you will, we are interested in mitigation of this liquefaction. So you think in that direction, and our listeners or other students will also give us the feedback regarding that, and we will come to you once again for that
nice.
part. So I think that this is part 1 is over, I understand. And for the part 2, we will meet once again.
Oh, definitely. It will be a pleasure. And it's always an honor. It's always an honor. And
No,
you have been a wonderful friend of mine. And I know the way you take geotechnical engineering, the way you create awareness is excellent. Thank you. Very nice to see you, sir.
Thank you. Thank you very much, sir. Thank you very much. I hope that all the students and those who have listened this, they are surely are benefited, and we will continue it in this direction. And very shortly, I think we will come back once again with the mitigation problem also. This so
All
that
right.
this topic is practically well covered in all respect. I think Solanki sir will throw some light on it.
Okay.
Professor
I see
S.K.
Dr.
Prasad.
Anand also. Hello, Anand.
Hello,
Yeah. Hello, sir.
Professor S.K.
Sir,
Prasad.
hi sir, hi sir, hi sir.
Thank you for the wonderful and informative presentation. We thank Dr. D.N. Naresh, Professor Ramaswamy, Dr. A.P. Singh, Dr. Parth Sarthi, Dr. Bablu Chaudhary for attending this webinar to be delivered by Professor S.K. Prasad. Professor N.K. Samadhya, President of IGS, could not join here due to the other engagement at the IIT Roorkee. We thank Engineer Hitesh Desai also for his presence here. He is the chairman of the Indian Geotechnical Society Surat Chapter. It was a wonderful presentation. We had a large audience here. We have participation from India, Tajikistan, Philippines, Taiwan, Malaysia, Bangladesh, Uganda, and Sri Lanka. I request Professor S.K. Prasad to answer some of these questions as come in the chat. So,
Sir, I will read the questions.
okay, you start
Okay, sir.
reading.
Yes, sir. One of the question is, can you tell how liquefaction is related to frequency of vibration? I mean critical frequency.
Basically, whatever be the vibration, when liquefaction happens, soil will be liquid. So, that vibration will not be transferred later on because, shear waves which are traveling in ground, when a ground becomes liquid, there will be no wave at all. And hence, it will become still. So, so what is the critical vibration or critical frequency, you ask? The critical frequency which can cause the water in the pore water space, to get the excess pressure is critical. That's all. So, what you require is, number one, large shaking. The amplitude of shaking should be large. Number two, the duration of shaking should be large. If it is for a momentary period, liquefaction cannot happen. So, shaking, during the rigorous shaking, at least it should be about 30-40 seconds. So, then you can expect the liquefaction.
Okay. How can age effect be incorporated in the analysis?
Till now, it has not been done. So that is why I wanted you people to think of probably some research on that. So age, I'm not talking about, geological age, million years and so on. I'm only talking about age of a filled up soil. So 100-year-old soil, it experiences some amount of, permanent, stable position in the ground. And there will be definitely, some resistance to movement. The particles will show some resistance to movement. And that is what is to be studied. And it has not been incorporated so far. And this is where, some research can happen.
Okay, sir. What is the probable reason which affected Surat and Bharuch more than Ahmedabad due to Bhuj earthquake? To reach Bharuch and Surat, earthquake waves has to pass through Gulf of Khambat, and the shear waves can't travel through liquid, and other waves are not that destructive than shear waves. So what is the probable reason then that more destructive effects were observed in Surat and Bharuch than Ahmedabad?
I'm sorry, I have not done this study. I'm sure, Manali must be working on that. Maybe in my next lecture, I'll be able to talk about it. So I have, relatively no idea what exactly happened here. See, one thing is very interesting. I told you very briefly about Michoacan earthquake in Mexico, which happened in 1985. 400 kilometers away, near the coast on the west, earthquake happened. The waves traveled all through for 400 kilometers, and unfortunately the ground in Mexico, it is soft clay. It is basically the volcanic ash, and the thickness of that is more than 50-60 meters. So the ground motion amplified there. So the level of acceleration when it reached the city of Mexico was less than 0.1 g. So it was not going to cause much problem, but it amplified by more than 5 to 6 times and caused rigorous shaking there. So if at all major problem has happened in Bharuch and Surat, it is because of the overburdened soil. So we'll have to study the type of overburdened soil. We'll have to try to understand what is the groundwater table and what kind of soil exists, and is there any scope for amplification in ground motion. I'm very sure Manali must be doing some studies on that, and I'll be happy to probably interact with her and then let you people know what was the reason for more damages that happened in Surat compared to Ahmedabad city. But interestingly, I have done some studies on Ahmedabad city. It is 200 kilometers, 230 kilometers away from epicenter. Epicenter was close to Bhuj. And, something like 100 buildings suffered severely. And they were all, 5 to 10 storied buildings, and they suffered. It is not because of liquefaction, it is because of amplification in ground motion. Unfortunately, during that time, we did not have many accelerometers. Only accelerometer available was in the passport center in Ahmedabad city, and that showed an acceleration of 0.1 g. But somewhere close to the places where destruction happened, I am sure the level of acceleration was at least 0.25 or 0.3 g. So that is due to amplification of ground motion as well as maybe a possible near resonance situation.
Okay, sir. Next question. Clay size particles liquefaction study is taking time. How to overcome the problem?
Well, strictly, it is the silty soils which can liquefy. Clay size particles, yes, of course they can. But clay, because of cohesion, it will show some resistance to liquefaction. In general, clays do not liquefy as easily as silty soil or fine sand. So some more studies definitely are required. And whatever is the recent addition to determination of liquefaction potential, especially by Bolanger, Idris, they all talk about the fine grained soils, and then the plasticity index relating to liquefaction and so on. So generally, a soil with higher plasticity index shows good resistance to liquefaction.
Okay. And last question. After liquefaction, what would be the percentage decrease the strength of soil? Does there any correlation with respective silt content?
Oh, definitely, that is another scope for serious study. I already told you, in general, when a ground liquefies, we tend to think that, it will show more densification. But the New Zealand earthquake showed that, repeated shakings can cause, repeated liquefaction at the same place. Therefore, the soil would not have experienced same amount of density as we see in, laboratory. So there is definitely some extra study required to understand after liquefaction, it will not still experience the desired amount of consolidation or densification. So, that requires, what was your question? You repeat the question?
Wait a minute.
Please repeat the question.
Are there any correlation with respect to silt content?
Okay. So this is what, you can really try to understand. So there should be some relations to the size of the particles, some relations to the level of shaking, and some relations to the level of confinement. So, but that is again a good scope for study in future.
Okay. Sir, Mr. Rajesh Kumar has raised his hand. He wants to ask.
Yes, sir. Am I audible, sir?
Yeah, very much, sir. Very
Sir,
much.
is there any attempt to prepare a liquefaction map of India sort of things?
Yeah. Actually, a lot of this micro-zonation works. So several cities have been,
Particularly northeast places like Bihar and Bengal.
I know in some of the northeastern cities, micro-zonation is done. Again, Gujarat, it is done several places, Jabalpur, and some of the northern regions, Chandigarh city, Bangalore, Chennai. So wherever you do micro-zonation survey, one of the important things you do is, to find out the liquefaction maps. And that is very, very essential. New Delhi also it is done. So lot of places are there in New Delhi which are likely to be liquefied under rigorous shaking. So work has been done, but it is not done in a unified way. Most of the times work has been done in a research organization like IIT. They have not been combined, put them together, but work is going on.
Sir, there is
Joshi has raised the hand.
can I ask one more question, sir?
Please, sir.
If you do the bore log test, our code says that if the fines content is more than 10 to 15%, it is prone to liquefaction. But we get this fine content more than 10 to 15% in several layers. Some layers are having prone to liquefaction, some layers are not. That way it goes depth wise. So how to decide depth of the liquefaction in that situation?
Yeah, you can go through that, assessment of liquefaction potential. And I also told you the most vulnerable situations which can cause liquefaction. Number one, the ground should be very loose. Its relative density should be perhaps, less than 40%. Number two, it should be fully saturated. That means, groundwater table must be above that layer. Number three, the soil particles, preferably if they are fine sand, silt, having low plasticity, there is a possibility. And all these plus the kind of shaking. So if it is in zone 2, you don't have to bother. We can't expect, huge acceleration. Even zone 3, chances are less. Okay. So you should be able to identify, when you have a bore log detail, you should be able to identify what is the kind of soil. If it is clay, if it is stiff clay, you don't have to bother. So SPT N value less than 10 is very vulnerable. And then what is the plasticity, content of that? And is it a saturated sand and soil, ground? And what is the relative density? So these are the things which will give you idea. So additional, information will definitely help you to identify, the zone of liquefaction. And then, we have a very simple rational method of identifying factor of safety. You find out strength versus stress. So stress you determine based on the future earthquake. Strength you correlate with SPT or CPT. And whenever the factor of safety is more than 1.5, you feel confident. If it is close to 1 or less, then you take a call.
Okay, thank you, sir.
Yeah. I think.
Sir, I am having one question.
Yeah, Manali.
Actually, sir.
1 minute, Manali.
Yes, sir.
Surat Joshi has raised the hand. Let him give the chance to speak.
And also, Dr. A.P. Singh has raised hand.
Yes, sir. Yes, sir.
Manali, I will definitely answer your question.
Yeah.
Sir.
Thank you, sir.
Sir, very good morning to all of you. More than any question, I am Dr. Surat Joshi from IGS Hubli Dharwad chapter. Prasad, sir.
Yes, sir. I know. I'm very happy and I'll be seeing you at 4:30 today.
Yeah, definitely, sir. More than any question, I just wanted to compliment you, congratulate you for the way you elucidated the things, and you are a master communicator.
Yeah.
The things
Thank
that
you.
have
Thank
to
you
be
so
put
much,
to
sir.
different sections of the audience have been aptly put by you, and it's very clear from the questions that everyone is having with this. The list that you gave regarding the liquefaction that will be aided by for certain parameters. One more parameter is the particle size distribution. A well-graded soil or uniformly graded soil is more prone to liquefaction
Correct.
than the well-graded soil, apart from not the actual size, but the grading of the soil
Yeah.
particles.
And
That's
well
one point.
graded, even shape also. As
Yes,
you
sir.
know,
Yes,
an angular soil is less vulnerable.
yes, sir. Yes, sir. Yes, sir.
Dr.
So,
AP Singh,
Yes,
once
sir.
again, my compliments to
Namaskar,
you,
sir.
and we'll meet in the afternoon.
thank
Yes,
you,
sir.
Sarat Joshi.
Thank you, sir.
Thank you, sir. Thank you.
Dr.
Yeah,
Dr. AP
Dr.
Singh.
AP Singh, please.
Sir,
Dr. AP
namaskar,
Singh.
sir.
Namaste, sir. Namaste.
Very nice, sir.
Nice to
I
see you.
listened all your lectures, and I try to attend all your lectures wherever,
I am
whenever,
honored, sir.
and wherever you are delivering, because it's always a learning this thing, learning lectures.
Oh, thank
Even
you.
for
No,
us.
no. You are such a knowledgeable person. If I hear from you, I feel very humbled.
Thank you, sir, for your compliment. Yeah. Sir,
Very
okay.
nice.
So
I just want one clarification from you, sir.
Please, sir.
Regarding the liquefaction potential analysis, there is no clear-cut,
Yeah, I agree, sir.
criteria, clear-cut criteria for the soil having clay content or the clay content.
Correct. Sir.
IS 1893 doesn't speak about
Oh,
it.
no. IS 8 doesn't speak. Probably you
And
can refer to
IRC, IRC 114208, that says something, that has given a one paragraph, and it also again a very confusing statement that the sand having a clay content greater than 25% with PI more than 10.
Correct.
What happens actually in the field, even with 10%, 15% clay content and some silt content, we get PI more than 10. So in that case, again, the proof consultant or somebody who is checking, he takes benefit of this and he says, no, you have to do the liquefaction, you have to calculate the factor of safety against liquefaction, and that comes less than 1. So what is your opinion about this? This statement is correct or some misleading? That's what if it is misleading, then what is correct?
You are very right. Actually, IS as well as IRC, they have still not addressed many of the things. So IS clearly says, based on 1971's Idris and Seeds approach. So maybe if you refer to Boulanger Idris approach of 2008, perhaps you should be able to come out with a more clarified solution to it. But these are all still very, very confusing. Chinese way of looking at is, if it is having higher plasticity, no, it will not liquefy. But recently, that has been given much more rational approach by a few of the scientists, Yaud and then, Boulanger. They have come out with a good solution. Maybe we should refer to that. And sometimes whenever it is in the border, 1.1 like this, depending on how important the structure is, we have to take some rational decisions, sir. So there is scope for improvement in that.
Yes.
But, so if you are very sure factor of safety is much more than 1.5, maybe all right. But whenever it is in between, I think we need more clarity. And that is when you may have to look at how important the structure is and take a better decision. And I would say don't refer to IS in that case, refer to the newer models. So I simply vouch for Idris Boulanger model of 2008, which is easily available. So that takes into account many factors. And if that also gives factor of safety marginal, you have to be a little careful. That's the only suggestion I can give.
Yes, sir.
Hello.
Thank you very much, sir.
Thank you, Professor Prasad. Thank you, Dr. A.P. Singh. Now I request most active Indian Geotechnical Society member Nazim Ali, who is research scholar of our institute and executive committee member of the Indian Geotechnical Society Baroda chapter, and also leading a student chapter of SVNIT Surat, for a vote of thanks.
Sir, anyway, before that, Manali had a question. Very quickly, you can ask your question. I'll try to answer as short as possible.
Okay, sir. Actually, I did the MSW test in the entire Bharuch region. At the 100 locations, I performed the MSW test. So, sir, how could I relate those shear wave velocity, and how can I correlate with the shear wave velocity with other methods?
Yeah, shear wave velocity is good enough for even liquefaction studies. Okay,
Yes, sir.
there is a correlation between SPT, CPT, shear wave
Yes.
velocity, and all these things. So you can use any of these models only. So from MSW, whatever, correlation for VS you got, you can use that, and hence you can try to find the CRR. There is no difficulty. So it is possible. You'll perhaps in the worst situation, you correlate with SPT and value. There are many empirical equations to correlate. Okay.
So can I generate my own numerical relation for that particular Bharuch region?
I think it is better. I think you should do that, and maybe we can discuss sometimes on this issue. And
Yes,
if
sir.
you are doing that, I'm happy about it. So you can let me know, and
Yes, sir.
whatever little I know, I will be able to share with you. Okay.
Yes, sir.
All
Yes,
right.
sir. Thank you, sir.
Okay. Yeah. So my sincere thanks to every one of you, my very good friend Professor Solanki, and it has been wonderful day for me, having talked to all of you. Listening to your questions, I knew that all of you are very much aware of this topic of liquefaction. So thanks to SVNIT. Please do convey my regards to Professor Gandhi, and that's it from my side. Nazim Ali, you can take over.
Yes, sir. As we refer to the comment section, you will be able to see that most of the participants have written that your session was very informative and it was a very excellent session. So I would like to convey that thing only, that your session was very informative and excellent session. You have explained very lucidly about the liquefaction risk management, and I hope that all the participants who have attended this webinar will be benefited from this. So on behalf of Indian Geotechnical Society Surat Chapter and Indian Geotechnical Society SVNIT Student Chapter, I thank you, sir, for accepting our invitation to deliver this lecture. Thank you,
Thank
sir.
you.
Thank you all the participants and speaker. Thank you all. So we end this meeting here. Thank you.
Thank you, sir. Thank you all for joining.
Thank you very much.
Thank you very much, sir.
Thank you.
Thank you, sir.
Good.
Thank you, sir.
Thank you, sir. So if you permit me, can I leave?
Yes, sir.
Yes, you may leave, sir.
Okay. Thank you, every one of you. Thank you, SVNIT. Thank you, Surat.
Thank you, sir. Thank you, sir.